Bismillahirrahmanirrahim. Assalamu alaikum, dear students. This is lecture on Lab 9 Supervised Learning, and we'll be specifically discussing convolutional neural networks, specifically in this part of CS351 Lab, Introduction to AI Lab. So, the contents are designed by Dr. Saeed Anwar, but I'll be delivering these for this demo. Okay, so what are the learning outcomes? After the successful completion of this lab, the students will be able to understand and explain layers, feature maps, max pooling, and fully connected layers. So that's the first concept that you need to know very well. The second concept is you should be able to train the specified convolutional neural network architecture for the MNIST handwritten digit recognition problem and report the training and inference results with training, validation, and test sets. Thirdly, you should be able to perform inference with a pre-trained model to understand importance of transfer learning. Okay, so for this lab, what you need to do is you need to have a computer with Python software, and I can basically then focus on this lab then. So MATLAB has a built-in toolbox by the name of Deep Learning Toolbox. It is formerly known as Neural Network Toolbox. It provides a framework for designing and implementing deep neural networks with algorithms, pre-trained models, and apps. You can use the convolutional neural networks, for example, ConvNets or CNNs, and long short-term memory LSTM networks to perform classification and regression on image, time series, and text data. Apps and plots help you visualize activations, edit network architectures, and monitor training progress. For small training sets, you can perform transfer learning with pre-trained deep network models, for example ResNet 101 or GoogleNet or VGG19, etc. and models imported from TensorFlow, Keras, and Caffe. So in this lecture, we'll basically be talking about convolutional network, what it is. We have already studied that in the theory course, so I'll not go into detail of the convolutional network here, but what you know is that a convolutional network is nothing but unlike CNN, artificial neural network, it is just divided into two parts. The first part, shown here, performs feature extraction from the input image, while the second part acts as classifier or CNN. So CNN has three types of different layers. It can have convolutional layer, it can have pooling layer, and it can have a fully connected DNN layer. So the first part here is feature extraction, the second part here is classification, and the convolutional network with basically this is a network that has got 8 layers. You can see you can name each layer by its prefix. For example, C represents convolution, S here represents subsampling, and finally F here represents the classifier layer. So the layers C1 to C5 and C5 to C7 constitute the frontal feature extraction and classifier parts respectively. The proposed work represents the depicted architecture with a string of 1 at the input layer, 2 at the C1 or the classifier layer, convolution layer, similarly 2 for the third layer, which is a sampling layer, and so on. And each number denotes the count of feature maps in that layer. Okay, so what is the convolution layer? Convolution layer is basically the core building block of CNN, where most of the computations are actually going to be conducted. It maintains pixel relationship by learning features using learnable weights matrices called kernels or filters. The input image is convolved with the kernel, and the resulting signal is called feature map. The convolutional layer in CNN learns features which are important for classification. It is important to note that correlation is different from convolution, of course. The kernel needs to be flipped vertically and horizontally before computing the dot product. The following figure shows a simple convolutional layer of CNN. A 5x5 image is convolved with 3x3 kernel, and the resulting signal feature map is shown in size 3x3 over here. So how do you create a simple deep learning network for classification? Here's an example and here are the commands that you're going to use. The example shows that how to create and train a simple convolutional neural network for deep learning classification. Convolutional neural networks are essential tools for deep learning and are especially suited for image recognition. The example demonstrates how to load and explore image data, define the network architecture, specify training options, train the network, and predict the labels of new data and calculate the classification accuracy. So for loading and exploring image data, here are the commands. You can just run them and check that they work fine. Then we are going to calculate the number of images in each category, and label count is basically a table that contains the labels and number of images having each label. The data store contains 1000 images for each of the digits 0 to 9 for a total of 10,000 images. You can specify the number of classes in the last fully connected layer of your network as the output size argument. So this is how you're going to do it. Then to specify training and validation sets, there are some certain parameters that you need to set, and these are going to be set in this particular manner. Then we need to define the network architecture. For defining it, you need to specify the image input layer. Then you need to define the convolution to 2D layer. Then you need to define the batch normalization layer, then the ReLU layer, then the max pooling 2D layer, then convolutional 2D layer, and so on. You need to define all of these and combine together. This forms the architecture of your CNN. So the image input layer is basically where you specify the image size, which in this case is, for example, 28 by 28 by 1. These numbers correspond to the height, width, and the channel size. The digit data consists of grayscale images, so the channel size, color channel, is basically 1. For a colored image, the channel size is usually 3, referring to the RGB values. Okay. Similarly, you've got the convolutional layer. In the convolutional layer, the first argument is filter size, which is the height and width of the filters. The training function uses while scanning along the images. Similarly, for the batch normalization layer, it normalizes the activations and gradients propagating through a network, making network training an easier optimization problem. So we need to use batch normalization layers between convolutional layer and non-linearities such as ReLU layers to speed up the network training and reduce the sensitivity to network initiation. Use batch normalization layer to create a batch normalization layer, of course. Similarly, you need to define the ReLU layer, the max pooling layer, the fully connected layer, and the soft max layer. Each has their own function that you've already studied from your theory class, and I'm not going to emphasize on these at this point in time. And finally, you have got the classification layer, which is the final layer, and this layer uses the probabilities returned by the softmax activation function for each input to assign the input to one of the mutually exclusive classes and compute the loss. So how to specify training options? In training options, you can basically set a couple of options that you can use for training. So we want to train the network using stochastic gradient descent with momentum, SGDM, and that you can specify here with an initial learning rate of 0.01. We set the maximum number of epochs to 4, and epoch is basically a full training cycle on the entire training data set. We want to monitor the network accuracy during training by specifying the validation data and validation frequency. We will shuffle the data in every epoch, and the software trains the network on the training data and calculates the accuracy on the validation data at regular intervals during training. And these are the different settings. Then we need to train the network, and for this we'll use a age-old command. We can use CUDA as well, and which are basically GPU with computing capability of 3 or higher. If a GPU is available, it will use it, but if it's not, so it's not going to use it. So for example, here we need to specify the training networks. Train networks is the function, and then we specify the IMDS train, the different layers, and then give it the different options. So for classifying validation images and computing its accuracy, we can use the ypred and classify function and IMDS validation dot labels to validate them and finally sum up the whole accuracy. In this case, after we run all these code, the accuracy is 0.9924, which is 99.24% of the validation data is correctly classified by our neural network. and that's a lot of accuracy increase. So with that, I think our lecture comes to an end. You should be able to use these commands to train your own dataset, and then now you're ready to go and perform the class tasks. Thank you very much.